Hello, everyone, and welcome to the August Recreational Astronomy Night meeting of the RASC Toronto Centre. My name is Paul Markov, and I will be your host for this evening, coming to you live from Markham, Ontario. We are online this evening due to the closure of the Ontario Science Centre, for those of you who haven't heard. However, our president, Tom Luton, will give us an update on a new meeting location during the announcements at the end of the presentations. Online meetings are made possible by our awesome AV team, comprised of Andrew and Betty Reed, Ward Legros, and Ennio Ciolucci. Regarding future meetings, there is one open slot for the September 4th meeting. We also have open slots for later meetings, which happen on the first Wednesday of each month. If you have a presentation in mind, please get in touch. The speakers for this evening are as follows. Arnold Brody will present The Sky this month, followed by Peter McMahon, and he'll tell us about what's new at Kitt Peak National Observatory, a Canadian look behind the scenes. And Pavel Krasnopolski will wrap up the evening's presentations with a presentation called Beware the Red Light. If you're watching us online and have a question for our speakers, please enter it in the YouTube chat box, and Ennio will ask the question on your behalf. If you're watching us online for the first time or not, please let us know where you're from through the chat box. Let's get the meeting started with Arnold and The Sky this month.
All right. Well, thank you, Paul. And thank you to the AV team of Betty, Andrew, Ward, and Ennio. You guys are awesome. And hello, everyone watching tonight. I'm in Whitby, Ontario. And for the next half hour, I'll talk about what's up in the sky for the rest of August and the first few days of September, up to our next meeting on September 4. Now, this month, we have the Milky Way rising like steam from the spout of the teapot in Sagittarius. You can run a mini Messier marathon with 40 Messier objects up in August, and you can do a finest NGC hunt with 11 targets up this month. And we have the Perseid meteor shower, a bright binocular comet, Saturn nearing opposition, a super moon, and an angry sun. There's a lot to cover this month, so let's get started. I like to combine astronomical twilight with night in what I call the observing window, since planets and bright deep space targets can be observed during astronomical twilight. The window is expanding rapidly between tonight and September 3rd, as you can see by the widening of the dark area in the hourglass between those two dates. It's widening quite rapidly. And because of that, the observing window that's currently 7 hours and 20 minutes as of tonight, it will stretch by nearly an hour and a half to 8:48 by the beginning of September. And night also grows almost 6 hours tonight, but over 7.5 by month's end. New moon happened just yesterday. So dark skies with little or no moon interference is with us now for the next week or so. The next dark period starts the last week of August, with new moon on the Labor Day weekend or the day after it. Now, the full moon on the 19th goes by a number of names. The sturgeon moon, the Cree called it the flying up moon because young birds would be old enough come August to jump and fly. The August full moon is also called the corn moon, or the ricing moon, the black cherries moon, and is also known as the lightning moon. Okay, let's begin our tour of the night sky with a look at the inner solar system. From Earth's perspective tonight, Venus and Mercury lie on almost the same line of sight. East of the sun, might they be visible after sunset? We'll check that out. Mars, meanwhile, sits almost 64 degrees west of the sun, rising 4 3/4 hours before sunrise. The air is steady before sunrise, so will Mars reveal details under high magnification, or are we still too far away from that little planet? We'll see. Here's how the inner four will move this month. On August 18, Mercury reaches inferior conjunction, passing between the Sun and Earth. And by the start of September, the speedy little planet will reach greatest elongation west of the Sun, easy to spot in the morning sky. Here we see Mercury and Venus 6 minutes after sunset tonight, but with atmosphere disabled, in other words, no daylight showing. And as we expected, Venus and Mercury do appear near each other, just 5.5 degrees apart. Mercury at this moment is just 2 degrees above the horizon. Venus is 3 times higher at 7 degrees 18 minutes above the western horizon. But with daylight restored, Mercury disappears while Venus can still be seen. Venus will appear essentially full at 95% illuminated. You might try using a moon filter to dim the planet down to better discern its limb. And if you have a minus violet filter, you can try that to remove any false colors created by refraction in the thick atmosphere near the horizon. Now, having just emerged from behind the Sun, Venus will orbit further east and be the evening star throughout the rest of this year, reaching greatest elongation east in January. Tomorrow night, Venus's elongation from the Sun is 17 degrees 40 minutes east. But by Labor Day, Venus will have moved 24.75 degrees east, though the ecliptic in the evening flattens and minimizes Venus's climb up the sky. With the Sun at the same depth below the horizon in these different pictures, Venus is only 1 degree higher by the start of September, although 7 degrees further from the Sun. Here's Mercury in the morning on September 3, just 1 day before greatest elongation west. The following morning, Mercury will be at the crest of this roller coaster-shaped orbit. Mercury is 7.75 above the horizon, degrees above the horizon, when the Sun is still 8.5 degrees below. And that's at 6 a.m. So it's going to be very easy to see Mercury during and just after Labor Day. Very easy. But those watching from the southern hemisphere, Mercury will be more challenging to find on September the 3rd. Here's the scene from Argentina. An hour and 15 minutes later, local time, the Sun is 5.8 below the horizon, 5.8 degrees, but Mercury is only 2.5 degrees high, and that's because the ecliptic intersects the horizon at a shallow angle winter mornings in the southern hemisphere. Here's where we can find Mars, rising in Taurus a few hours ahead of the Sun and not far from Jupiter. It will glow around first magnitude depending on its altitude. It is still a small dot, appearing just 6 arcseconds wide. And when we catch up to Mars 6 months from now in January, it will still be fairly small at almost 15 arcseconds. That's because winter oppositions with Mars are poor when the red planet is near its aphelion. Good opportunities are in late summer, and 10 years from now, we finally get one on September the 11th in 2035, when Mars will appear 70% larger, nearly its maximum of 25 arcseconds. At 6 arcseconds now, can details be detected on Mars? Well, maybe, if we can trust the scene from Stellarium. Here we're pushing an 11-inch SCT over 1,000 times magnification. That's like 100 times per inch, and I think 50 per inch is typically the rule of thumb. So I'm not so sure this can be trusted, this scene here. We're probably going to have to wait until the winter time when we get a bit closer to Mars to be able to see some detail on it. Here are the positions of the outer planets along with Earth and Mars as of tomorrow night. From our perspective, Jupiter appears close to Mars, as we already saw. Saturn, meanwhile, appears almost a quarter of the way around the sky from Jupiter. Saturn appears to be around 6 hours ahead of Jupiter in terms of rising, transiting, and setting. Indeed, Saturn transits the meridian at 3:30 later tonight, and Jupiter transits at 9 a.m. That's 5.5 hours later. Uranus should appear near and west of Jupiter. It looks to be around 3 weeks ahead of Jupiter in terms of opposition, and Neptune looks to be around 2 weeks behind Saturn. Well, here are the next opposition dates for the outer planets. Uranus is 3 weeks ahead of Jupiter, just about, and Saturn is 2 weeks ahead of Neptune. As we expected, Uranus is near and to the west of Jupiter this month. That's Mars near Jupiter inside the horns of Taurus the Bull. Jupiter is getting progressively brighter and bigger as we orbit towards the gas giant. It's now -2 in magnitude, though you'll lose a magnitude or so depending on how low it is in your sky. And if you are fortunate to have good eyes, you might be able to pick out the tiny disk of Uranus around magnitude 6. This is how Jupiter will look this weekend, with an apparent diameter of 36.2 arc seconds. By month's end, it will grow 6.5% to 38.6 arc seconds. And you might like to try using a light blue or light green filter when observing or sketching Jupiter. These filters will darken the reddish cloud bands and, of course, the great red spot. That will increase their contrast and improve their visibility. There's a fun sequence of events involving the Galilean moons Io and Europa on Friday morning, August the 23rd. The moon Io will cast its shadow on the planet before transiting across itself. While transiting, it will kind of disappear into the brightness of Jupiter. And while that's happening, Europa is going to enter the shadow of Jupiter. The shadow of Jupiter goes off in this direction. Europa will enter it, disappear, and then reappear just before going behind the planet. Here's a video showing you that. Watch now here as the shadow of Io should appear. There it is. You can see it on top of a cloud band. Io has disappeared. Europa is now in the shadow. And as Io reappears, so does Ganymede, Europa, I meant, and it just disappeared. If you may have seen that, I'll show you that again. There's 6 minutes in that circle there. Watch, it's going to be faster than 6, but there's Europa reappearing, and in 6 minutes time, real time, it just disappears. That might be a fun thing to try and catch. Uranus is bright enough to be seen without optical aid on a dark and transparent night. Magnitude 6 is considered the dimmest we can see, and Uranus is brighter at 5.62, although atmospheric extinction will drop it back down to the 6th magnitude range. So I recommend you wait as long as possible. Here we are at 5 o'clock, by which time Uranus is 48 degrees in altitude, and that'll improve your chances of being able to spot it. To help you find it, look for a blue dot a little over 5 degrees southeast of the Pleiades. You can use binoculars to confirm the location of Uranus and then try without. This stellarium scene includes stars down to magnitude 5.6. And there you can see there is a star that's going to help you out, not far from Uranus. You can find Neptune and Saturn rising in the southeast once the sky darkens. Of course, you'll need binoculars or a telescope to spot Neptune. Butterscotch Saturn will shine around magnitude 0.71 or less due to our atmosphere. Now, a few years ago, when Saturn's rings were tilted wide, the dot of Saturn appeared about 3/4 of a magnitude brighter. That's because the rings were tilted wide, adding their bright reflection of sunlight. They're as bright as the planet itself, so that would definitely make the dot appear brighter. When I saw Saturn in the sky with my eye, it did look as though that dot was a little bit dimmer than I'm used to seeing it. And Neptune has the tiniest apparent diameter of all of the planets at just 2.4 arc seconds, but with with sufficient magnification, you can perceive the planet's disk shape and blue color. Saturn's rings currently appear like a line drawn through a circle, imitating a double star symbol in star atlases. It is a very unusual sight, a weird sight in your eyepiece. The ring tilt has narrowed to less than 3 degrees on its way to 0 as we pass through the ring plane 8 months from now in next March. Saturn's biggest moon, Titan, is the 8th magnitude dot, sharing the ring plane. And you can try using light yellow or yellow-green filters to improve contrast in the cloud bands and help them stand out. They're so hard to see otherwise. Now, regarding Comet 13P Olbers, it's cruising its way out from the inner solar system, having passed perihelion 38 days ago on June 30. Its high inclination of 44.7 degrees sends it north of the ecliptic plane after perihelion, keeping it above the western horizon after dark for quite a bit of time, around 2 hours. As of yesterday, the comet is glowing at magnitude 7.3. Now, 7.3, that's too dim for naked eye, but easy in binoculars. And here we see its path over the next 4 weeks, each dot representing its nightly progression, and it will cruise by a couple of deep space targets on its way. On August 29, there's a tempting close encounter of comet Olbers with globular clusters NGC 5053 at magnitude 10 and brighter M53 at magnitude 7.6. Olbers should be around magnitude 9 to 10 in late August, similar to 5053, and all three fit comfortably in a wide field of view. A nice low power imaging opportunity. Olbers' orbit doesn't bring it particularly close to Earth with a perigee of nearly 2.5 astronomical units. However, its path high above the ecliptic explains its visibility well above the western horizon after dark for northern observers. And as the comet passes through the plane of the ecliptic, it appears to pass across Mars's orbit. Is that simply superimposed like it is in front of Earth and Venus's orbit, or is it really that close, tight? Well, if we change our perspective, when we tilt this orbital plane a bit, we can watch to see, and sure enough, it does look as though the orbit of Olbers is right up tight against the orbit of Mars. In fact, the two have a separation of 0.3 AU. That's about 10 times the Earth-Moon separation, but it's still quite close. And as a result, there are meteor showers that strike the southern hemisphere of Mars every time it passes that spot in its orbit. Something to keep in mind if you want to build a moon colony, a Mars colony, you're going to probably want to stick to the northern hemisphere. Now, speaking of meteor showers, the Perseids began a few weeks ago in mid-July and runs till mid-August, with its peak occurring on the night of August 11-12, which is this coming Sunday night into Monday morning. The moon, one night shy of first quarter, sets at 11:17 and does not interfere with the peak of the show, when up to 80 or maybe 90 an hour could hit our upper atmosphere. That would be 1 or 2 a minute. Now, while the moon is still up, many astro imagers will aim video cameras at the moon on tracking mounts because the unlit western side of a first quarter moon is also facing the Perseids. And without an atmosphere, the Perseid meteoroids become meteorites in a flash that you can capture. They do hit with the energy of 100 pounds of TNT. They will make a bright flash, and hopefully your video camera frame rate is fast enough to catch it. The parent comet of the Perseids is Swift-Tuttle with a 133-year orbit. last visiting the inner solar system in 1992. Now here's an all-sky view. As we approach midnight, we begin to rotate into the direction of our orbit around the sun, which is that green line you see. Notice how our orbit heads in the direction of Perseids radiant, while at the same time, the radiant climbs towards the zenith, at which point we're plowing headfirst into the debris stream when your chances improve of seeing 1 or 2 meteors a minute. The sun now, at local noon, it descends a considerable 8 degrees and 40 minutes over the next 4 weeks, which explains that big jump in the observing window I talked about earlier. Activity in the sun's southern hemisphere over the past month, especially from active region 3762 that has just rotated out of view around the sun's eastern limb. Adjacent active regions have interconnected magnetic field lines, so an outburst of flares in one can trigger an outburst in another. Last week alone, there were over 14 strong M-class flares and 1 X-class as 3762 traded punches with those other southern active regions. The activity will continue with more regions growing as they rotate to 3774 and 3780. 3774 is taking aim at us pretty much right now while growing considerably in both the number of sunspots and size. It has strong potential for C-class flares and moderate 35% chance for M-class. Even more impressive is 3780. It's a monster, 3 times as large as 3774 and still growing. Its sunspot number is also growing, and it includes what are known as delta spots, where positive and negative umbra share the same penumbra. Now that's intense. M-class at 50% probability and X at 15% already. I wonder if it will continue to grow as it rotates towards us. This chart from the NOAA Space Weather Prediction Center shows actual versus predicted sunspot counts thus far into solar cycle 25. And you'll notice that actuals have exceeded expectations since the cycle began. Statistics gathered for July show a count of 196, nearly double their prediction, and far exceeding the cycle's expected maximum next year, at least according to the NOAA. When solar cycle's maximum has actually occurred can only be determined a few months after we have passed it, because some cycles experience twin peaks, or 2 maximums a few months apart. So the count may go down and then back up again before going down and staying down, at which point we can determine when that peak happened. If you get 2 peaks, it's because one of the poles, the positive or negative, settled into its permanent position, into its home position, while the other pole is still searching for home. And that's when you can get 2 different peaks. Now on to the moon. Our moon reaches apogee on August 9 at 405,000 kilometers from Earth. When full on the 19th, it's almost at perigee, reaching 98.5% of its perigee size, making this a supermoon. Perigee is reached 2 days later on the 21st, when the moon appears 11% larger than at apogee, and new moon occurs on September 3, so we'll have dark skies on the Labor Day weekend. By the way, the full moons of August through November will all be supermoons. This coming Saturday night, 2 craters in the Explore the Moon observing program, Aristoteles and Eudoxus, lying near the terminator, are ideally illuminated for observation and can be studied together in the same field of view. Aristoteles is the older of the two and wider at 87 kilometers versus Eudoxus at 67. Both have well-defined and broad rims, nicely terraced. There is an interesting radial pattern around the northern rim of Aristoteles that you can see when the sun is at a very low angle. Neither crater sports a tall central peak. Aristoteles has an uneven rippled floor, while Eudoxus has a cluster of low hills on its floor. And if you're lucky, you can catch sunlight racing across the floor of Eudoxus, exposing those hills. And now it's time for close encounters of the moon and planetary kind over the next 4 weeks. The first, starting with the moon, setting 4.5 degrees ahead of Spica as the evening twilight darkens. On Friday, August the 9th, that's this coming Friday. And on Tuesday night, August 13, you can catch the moon only 1.5 degrees west of the red supergiant Antares, one of the largest stars known. It's 555 light years away and 10,000 times brighter than our sun. Maybe it would be possible to image the moon and Antares with globular cluster M4 positioned in between, but I'm not sure if the first quarter moon would wash out M4, but it might be worth a try. The next morning, you can watch Mars and Jupiter rising less than 0.5 degree from each other, possible to catch in the same telescope field of view, if it's a wide field eyepiece. In the evening of Tuesday, August 20, Saturn has a close encounter with the Sturgeon moon. You can catch them together in a wide field with the limb of the moon just inside the field. On Sunday night, August 25, into Monday morning, the last quarter moon rises right behind the Pleiades, making for a spectacular sight. Hopefully, the brightness of the moon does not wash out the Seven Sisters. A dry, transparent night will help. And the following morning, Tuesday, August 27, the moon, Jupiter, and Mars rise in a diamond formation with Elnath Beta Tauri, a bright 1.65 magnitude star. And on Friday morning, August 30, you can catch the moon rising in a nearly straight line with Castor and Pollux. Those are the heads of the Gemini twins. Now, I mentioned at the top that August is a good time to observe Messiers and the finest NGCs. So let's compare 2 planetary nebulae and 2 open clusters found in the finest NGC and Messier catalog observing programs to round out tonight's tour. We'll work our way from north to south, starting with Planetary Nebula NGC 6445, found in northern Sagittarius, not far from the border with Ophiuchus. It's located a little over 2 degrees northwest of 58 Ophiuchi, a magnitude 4.9 star. Now, a planetary nebula marks the death of a sun-like star as its former shell of gas drifts off into space. The ejected shell is a type of emission nebula because the exposed core of the star, hundreds of thousands of degrees hot, energizes the expanding shell, causing it to glow. Planetary nebulae are small and frequently circular in appearance, causing Herschel Walker in the 1780s to famously say they resemble planets, and the term planetary nebula was coined. Now, NGC 6445, however, appears rectangular instead of circular. Perhaps it got its nickname the Little Gem Nebula because planetary nebulae are small, and this one resembles an emerald-cut gemstone. Maybe that's the reason. For comparison, the other planetary nebula is NGC 6369 found just inside Ophiuchus. If you star hop, you can start with magnitude 3.3 Theta Ophiuchi, hop a degree plus northwest to magnitude 2.7 Beta, and then another degree west to that dim 4.8 star C Ophiuchi, which is half a degree west of the nebula. The planetary nebula is round and planet-shaped and relatively faint at magnitude 11.4. The high-energy radiation from the central white dwarf causes the surrounding nebula to emit light from ionized oxygen, colored blue in this Hubble image. And the hydrogen looks green, and nitrogen would be red. Now, the little ghost nebula's round planet-like shape is visible under strong magnification, as seen in this sketch by H.D. Curtis back in 1918 at the Lick Observatory. The nebula should be visible with strong magnification. Here we're up to 337x. And the first of two open clusters is NGC 6520, also known as the Dead Man's Chest Cluster for reasons I could not find. You can locate the cluster around 1 2/3 degrees north-northeast of 4.5 magnitude Gamma 1 Sagittarii, or just over a degree northwest of an equally bright field star to the northeast there. 6520 is superimposed upon the large Sagittarius star cloud. It is magnitude 9, has a diameter of 5.4 arc minutes, and has about 25 stars of magnitude 9 to 12 in it. And the dark nebulae Barnard 86 lies right up against its western edge. Now, under good conditions at the eyepiece, this can be an amazing sight, like a sea of milk, punctuated by the cluster's bright stars and the adjacent inky black B86. That will create a fascinating view at the eyepiece. Now, B86 is one of the coldest regions that we know of in our galaxy due to its high density, blocking out any light from entering and heating up the dust. B86 is fluctuating, kind of like jelly, and it's apparently on the verge of collapsing to produce a star or two in a couple of 100,000 years. Now, the Trumpler's classification includes R, and R means rich, 100 stars or more, so there must be more than the 24 that we talked about at magnitude 9 to 12. So many of the fainter stars in this neighborhood are probably member stars of the cluster. And our final object, our comparison star cluster, is M7, also known as Ptolemy's cluster, and NGC 6475. Excuse me. The cluster has been known since antiquity. It was first recorded by the 2nd century Greek-Roman astronomer Ptolemy, who described it as a nebula in 130 AD. It is the southernmost entry in the Messier catalog, with a declination of minus 34 degrees. Summer is the only time to catch it from up north, but for those observing from the southern hemisphere, M7 is easily observed high in the winter sky, about 13 or so degrees from the zenith. And it can be seen sometime during the night on most months of the year from the southern hemisphere. Now, you can find the cluster around 2 1/3 degrees north-northwest of G Scorpii, though the cluster is really bright enough that you can probably find it naked eye, just looking north of the Scorpion Stinger. M7 is 200 million years old, a relatively young cluster. Its members include a diverse assortment of spectral types, mainly consisting of hot, luminous, and short-lived B-type and A-type stars. However, it also hosts a number of cooler stars more like our sun, G-type and K-type stars, making this cluster a popular site for exoplanet searches. The cluster's brightest star, a K-type giant, shines with a magnitude of 5.6. The hottest is a main sequence star of spectral type B6. And those B stars, they only live for a couple of 100 million years, so some of those might be ready to pop. The abundance of heavy elements or metallicity in the stars of M7 is comparable to that of our sun, meaning they all form from similar material, and that also increases the interest in finding exoplanets here. The cluster is by far the brightest of the 4 DSOs we've looked at, shining at magnitude 3.3, glowing like a nebula to the unaided eye. And under magnification, here we're looking at it through binoculars, the cluster's concentration of stars look like crisscrossing rows of bright stars surrounded by a scattering of more of similar brightness. Again, the Trumper classification includes R, meaning 100 or more, so many dim stars towards the center may belong to that same cluster. And that's a wrap. So are there any questions?
Arnold, thank you for another detailed and well-delivered presentation. Well done.
Thank you.
Let's go to Ennio. Do we have any questions for Arnold?
We have a couple of questions. First, a comment from Leo to CAF, who says, spotted Neptune last weekend of July. This prompted Betty to ask the question, would Neptune be easy to see with binoculars, or is a telescope necessary?
You know, at magnitude 7 something, it should be just as easy to spot either way, I would imagine. It's not like you're going to see any detail with a telescope. Although you might gather more light, it might be a little bit brighter. I'm not sure, but it should be visible either way.
Okay. Eric asks, please, what Starry Night Horizon panorama is that with the row of cars?
I'm afraid I didn't understand. Can you repeat, please?
So in Starry Night, you have a horizon with a panorama with a row of cars.
Oh, yes, that's right. It's one of the Starry Night choices from the landscape scene. I don't remember which one off the top of my head, but if you're playing around with Stellarium, you can definitely, it's one of the top 4, I believe.
Okay, and this just in from Ron McNaughton. Just before the meeting, I got an email that there was a G2 class flare with possible arrival on August 9th. How strong is that? And great talk.
Thank you. G2 flare. I'm familiar with the C, M, and X. I don't know what a G class might be. I'm afraid I'm unable to answer that question.
Fair enough. That's all the questions we have.
Okay, well, thank you. In fact, I'll try and look up what a G-class flare, if I can find any information, I can post it on our forum for those that want to check it out.
Okay, yes, please do.
Okay.
All right, thanks again, Arnold. Great presentation. And I hope that we're ready to go with our next speaker. Are we? Perfect. Good. So we have a special guest speaker this evening, Peter McMahon, and he is the manager of the Kitt Peak Visitor Center, and he's actually talking to us on site from Kitt Peak. So take it away, Peter.
All right. Thanks, Paul. Glad to see you guys, and hope you can see some of the observatories behind me here. A little bit of background. I originally was am from Peterborough and from Toronto. Went to Ryerson, now Toronto Metropolitan University, for journalism, and specialized in science journalism. Did some work producing for Discovery Channel and different science and geography magazines and astronomy magazines. And ended up, in addition to working for CTV News and Discovery Channel, and a number of other broadcasters and news outlets eventually moved to Jasper to co-found Jasper Dark Sky Preserve and the Jasper Planetarium and observatories there. I worked there for just under 9 years as the general manager there. I'm still a COMA winner there, so as you can imagine, we're anxiously awaiting news of how things are going down there. But meanwhile, last summer, my wife found a job ad for a management job with Uncle Sam down here in Arizona near Tucson. For heading up the visitor center at Kitt Peak, as Paul said. And so one thing led to another, and got a job offer, and we now live in on the outskirts of Tucson, which people sometimes mistake for Tombstone. That's a few thousand people. Tucson's like 1 million people, and it's just to my right. Phoenix is almost directly behind me, and we are about 1 kilometer above the desert floor, 2 kilometers above sea level. And I want to take the opportunity over the next, how are we doing here, 27 minutes or so, to take you on a tour of Kitt Peak. Rather than move around and risk the Wi-Fi going down, I've pre-filmed a number of things, and I can also turn my camera around and show you some of the other observatories. So I'll just show you real quick here. You should be able to see 3 or 4 or 5 other observatory domes here, and we'll come back to that in a little bit. I've got some close-ups to show you of those. I'll tell you a little bit and talk to you a little bit about the science, but mainly about, I want to take the opportunity to actually take you into these telescopes. And if you've got questions about the science happening here, or the engineering end of things, or just life up here on the mountain. I don't live here, but I do work here part of the week in downtown Tucson. I can tell you a little bit about that. We'll come back to this one, but the main telescope that you see behind me here, and I'm going to go on and off with my sunglasses here when the sun pokes out, is the 4-meter Mayall telescope. Some of you may have been to Kitt Peak before. For those of you who have, I want to give you a little bit of a update on what's new here from the perspective of a Canuck who's now living in Tucson, living in southern Arizona. And if you've never been here, I'll be really excited to show you a number of things. But like I said, if you have been here before, I'll also be talking about some of the things that are new, kind of slightly pre-COVID and post-COVID. That 4-meter telescope behind me, the building that it's in is about 200 feet tall, just under 200 feet tall. You can easily see it with the naked eye from downtown Tucson, from our house in the suburbs in western Tucson. We can see the detail between the dome and the telescope itself. And I'll tell you a little bit more about what's being discovered there. I'm just feeling a raindrop on my hand right now, and I'm going to roll the dice and hope we're okay, but you might have heard some rolling thunder as well. It is monsoon season, and I'll just turn around over here so you can see a little bit more of the sky heading towards us. If it gets really bad, I'll close the roof on this rooftop observatory that we're in. It's a 16-inch RC Cassegrain telescope on a roll-off roof. And while I'm looking around here, I'll just show you that direction. That is California, the very farthest mountain, if you can see, and then to the left, the far left before that, that gray ash dome there is Mexico. And you might also be able to see further down on the ridge. We may not have time to talk about all of those, but there are several radio telescopes, including a 75-foot radio telescope. So that's a little bit of the lay of the land. What I'd like to do is take you on a tour. I'm just going to spin this around and look with you to make sure you can see what I'm seeing. There we go. So the telescope just next to the larger telescope there in the distance. So I'll just put it in the center of the frame right there. That is our 2.1 meter telescope. And it's where decades ago, renowned astronomer Vera C. Rubin, who now has a state-of-the-art major observatory in Chile, who bears her name, did pioneering work in identifying the nature of dark matter. And sorry, that was just someone on the walkie-talkie say we're still fine to not shelter in place. It sounds like I'm good to be outside with you here a little longer. I'll just show you a quick visual view, a quick still view inside this observatory here. So I'm going to share my screen. Hopefully we're good with that. There we go. I'll tell you also, just while I'm getting ready to do the screen share, we were actually, scientists here are moving the mirror of one of the telescopes here. And that's actually, it's been re-illuminized and it's heading back soon in the next few days. There we go. I think we can see the, let me know if not, but we can see the view inside this observatory here. And this is the 2.1 meter telescope. And there we are, there we are a little zoomed out there. This was the first major telescope that was built at Kitt Peak in the early 1960s, 1962. The observatory was founded in 1958. And this telescope, and I'll just show you what, this is what visitors see. So this was taken next to the telescope. Visitors on site don't get to see that. There's a viewing gallery. And I was constantly amazed when I came here for the job interview process, and afterwards, once I started leading the visitor center at Kitt Peak, how much thought was put into public outreach, even from the get-go in the 1960s, in that a lot of the major telescopes here have viewing galleries that allow tours to happen without getting in the way of science being done, of calibrations and other things that are happening in the daytime. And then we have nighttime tours as well, and I can talk a little bit about that later. I'm also going to show you some of the daytime views of these telescopes. Okay, I'm going to stop sharing that. I'm going to show you one more telescope. There's going to be probably four that I'll take you inside. So that was one of the major telescopes, but not the biggest one by a long shot. The next one I want to show you is the Wind Telescope. And there's a lot of acronyms, but that stands for Wisconsin, Indiana, Yale, and NUORLab, which is an acronym in itself for the organization that runs Kitt Peak. It also stands for NASA now as well. And some of those universities have dropped off. Princeton has come on. But that telescope, I'm just going to move the view around here so you can see where that is live right now. And then I'll show you some pictures and video that I got earlier for that. So right in the distance, you'll see sort of a boxy telescope. Let me make sure I've got that right. There we go. So to the left of the telescope that seems closest, that's from the University of Florida. But in the distance, beyond that dome telescope that's right here in the parking lot of our visitor center roll-off roof telescope, you can see that telescope with a boxier, you could call it a dome over top of there. And I'm going to show you a video outside that telescope. That was not taken by me. Most of these were, but this was not taken by me. But it gives a really good sense of the mountain and this telescope as well. I'm just going to screen share that here. Okay, right on. We'll play this. We'll take a look at this view here that was filmed about half a year ago on site here. So this telescope here, the Wind Telescope, is, and we'll go inside it in a second, is basically responsible for characterizing, identifying the masses and densities of different dwarf planets previously discovered by the TESS survey. Here we go. You can also get a sense of the sheer height here. We're kind of, when you drive up to Kitt Peak, you're kind of driving up, spiraling up a pencil, and you park on the eraser, and we're on the eraser of the pencil right now. This is a 3.5 meter diameter mirror. And again, this telescope's mirror is actually being cleaned in the illuminizing chamber of the large 4 meter telescope that you'll see in the distance that's directly exactly behind it now. That telescope is home to a experiment that is probing the depths of dark energy, which I'll show you a little bit more about in a few minutes. But first, let's go inside the Wind Telescope. I'll show you a little bit of the close-ups of the mechanisms that are actually discovering not only the masses and densities of existing exoplanets, already discovered exoplanets around other stars. There's some of the radio telescopes there in the distance down the ridge, but also new exoplanets as well. Okay. So this is a look at the telescope inside, and what you'll notice compared to the 4-meter telescope, which is early 1970s era technology, this is mid 1990s era technology, much easier to get it into the smaller space. They realized that that height off the ground of 180 feet almost was not needed, and this telescope, there we go, there's the mirror there, is using an experiment called NEWID, which is spelled NEID. And that's essentially using a very high fidelity one fiber optic strand, as opposed to thousands on the next experiment I'll show you, to look at star systems and find out things about exoplanets, and even find exoplanets using the radial velocity method, i.e., looking at the wobble induced in a star and denoting that there is a Jupiter mass or bigger planet around that. Here's a close-up look. We'll actually look inside that NEWID experiment when they had it open for servicing a few months ago, and you can see a little bit of light in there. But this is basically off to the side of the telescope. This telescope has not adaptive optics, but it has optics where the surface of the mirror is changed on a second-by-second basis according to what angle it's pitched over on, to make sure it stays the shape it needs to in order to have that extremely, there we go, we'll just unshare the screen here, there we go, high fidelity way of detecting things swinging around distant stars, planets swinging around distant stars. The other really interesting thing about it is it's probably the loudest telescope on the mountain. It sounds like two semi-trucks racing each other down the highway, and that's because those are fans that cool cryostats that the fiber optic lines go down to feed information down to the brains of that telescope, the fiber optic line being the eyes of that telescope. After light from the main mirror hits that fiber optic in that experiment off to the side. I want to take you on a tour of our largest telescope now, and then we're going to end on telescope number 4. And if there's extra time, I can show you a few others, but we'll maybe do Q&A first if you've got any questions. So that's telescope number 2 of 4. Number 3 of 4 is the biggest telescope by far on the mountain. At the time that it was built, it was the second biggest telescope in the world in 1972. It's the Nicholas U. Mayall 4-meter telescope. And let me just go to some visuals of this, and I'll tell you a little more about it. I mean, you can see it. I'll tell you, it's behind me right now. There it is, live in the flesh. Again, 180 feet tall, 18 stories tall. You may be able to see, let's see, let me get my mouse arrow here, and I'll get my head out of the way. Right over here, there's a slight sort of white discoloration. That's a pickup truck. It's about that size, to give you an idea of scale. This telescope is creating, scientists at this telescope, using a new device mounted on it, are creating the largest, most detailed 3D map ever of the universe. This is 1970s technology, but the device mounted on it, DESI, which stands for Dark Energy Spectroscopic Experiment, is an almost brand new device. It was put on just before COVID, I believe either 2017 or 2019. Definitely was in use in 2019. But it went fully into use in earnest after COVID. It actually finished its mapping survey, the first phase of its mapping survey, early, and you can Google that and see YouTube video of these galaxies plotted out. I'll tell you a little bit more about that once we actually go into the telescope. So let's go do that. I'm going to screen share again, and I've got some visuals, some still images to show you that I took earlier inside this telescope to give us a sense of what it's like to tour these places without actually having to take the time for me to drive over and have the Wi-Fi drop out. So here we go. We're going to take a look at the inside of the Mayall 4-meter telescope here on Kitt Peak. There we go. So this is, let me just full screen this here. Most of the building you saw is not this, but this is a vast sort of, this is like a tenth the size of the Air Canada Centre. It's quite large inside. It's actually larger than it needs to be. The Department of Energy, U.S. Department of Energy, which runs this, is possibly going to be upgrading this to a 6-meter mirror. There's more than enough space in the Cassegrain cage to put bigger optics, and it's suspected that even though this telescope was slated to be divested between 2012 and 2016 and possibly bulldozed, the Department of Energy came along and said, we have this experiment that has 5,000 fiber optic cables, or 5,000 fiber optic lines that look like this right here. And I've actually got one of them here that I'll show you up close in my hand in a second. But these 5,000 robot positioners position 5,000 individual fiber optic strands in this amount of sky, so several degrees of sky, wide field. It's a prime focus telescope, but it turned out this was the only telescope available and beefy enough to take this 60,000 pound instrument that holds these robot positioners. Those positioners are basically pointed to this particular field of view, and each positioner positions a separate fiber optic line pointed at a particular galaxy to measure the spectra of that galaxy. And in doing so, it can find out things about that galaxy, how it is moving. You might hear some more thunder. I haven't seen flashes of lightning, so I think we're fine. How it is moving in respect to the galaxies near it as the universe expands, and map out where those galaxies are as they're expanding, finding out more about the expansion history of the universe and the nature of dark energy. So it's kind of cool. I'm going to undo the screen share here for a second, because I want to show you this is really neat. I'm going to stand up and hopefully not lose the laptop of its cable here. But across the valley, where we've seen this 2-meter telescope right over here, this was where Vera C. Rubin was pioneering, just in the middle of the view right now, was pioneering the exploring the nature of dark matter. And then across the valley, that work paved the way for the exploration and discovery of the nature of dark energy in the telescope behind me. I just think that's kind of cool. I'll show you before I go back to screen sharing. This is one of these robotic positioners. This is a broken one. That's why I'm allowed to have it. There are 5,000 of these. The whole experiment is, in Canadian dollars, is just under $100 million. That's just the experiment, that black part at the prime focus of the telescope, not the observatory of the telescope itself. But this positioner would sit in a pedal, sort of pie shape, with about 1,000 or so of these. This is missing the fiber optic line. The fiber optic line would be going along here. And you can actually see, if I hold it up correctly here, you may actually be able to see right through it if I hold it just perfectly here. And this is, okay, you can't quite see it, but through there, this whole thing is hollow. That's where the fiber optic line goes. It sits here. The fiber optic cable goes up here. And this little motor here, which is, I'll hold my finger up so you can see the size of it. A little motor with a little gear, that's it, there it is against my fingernail, is what positions one of the two axes for this fiber optic cable to move back and forth. The other axis is by this spinning back and forth. So this sits stationary in the pedal of 1,000 of these. There's 5 of them. And this moves back and forth and positions this fiber optic cable. So why does it position the fiber optic cable? It's to point it at a particular galaxy. This sort of thing, this sort of survey isn't new. I'll just go back to some of the visuals here while we're talking about this. This sort of survey isn't new. It's been done with the Sloan Digital Sky Survey and other such things. But those, excuse me, were using plates where there were basically holes cut out for where those galaxies were. So you would get the light from the galaxies, but not the stars. There's a much more impressive view of the telescope during a VIP tour. The public does not get to see this. There's a viewing gallery similar to that 2.1 meter telescope. So the public doesn't get to see this, but these are people from the National Science Foundation who fund Kitt Peak. And you can see the scale this is on. You can see the mirror. There's about 3.8 meters worth of usable, or sorry, 3.6 meters worth of usable space on that mirror. That light comes off the mirror into the prime focus of the DESI experiment here. And again, the way this used to be done is metal plates with holes punched out where the galaxies are would be put in, so you wouldn't get the light of stars, just galaxies. And every time you went to a different part of the sky to do these sorts of surveys, you would have to change plates. Eventually, they were robotic, sort of like the things that pour your drink and then move the drink along at McDonald's and other fast food places do for the plates to shift them in and out. That still took a while. But the cool thing is with this experiment, the reason it's so valuable is not just because it is able to view things in higher detail. There's the telescope on the side there, but that it's able to reposition to look at other fields of view so much more quickly. Because rather than moving the plates, those 5,000 robot positioners just reposition to known places in the sky where we want to be looking at galaxies, and off they go. So for that reason, there are tens of thousands of galaxies that are able to be plotted out each night, and millions of galaxies where only hundreds of thousands were before. Because of the success of this experiment, it's my understanding that the Department of Energy is likely going to be using this telescope until at least 2037, which is staggering to me in that it was facing the wrecking ball not too long ago. Just to show you how it works, I'll just take a closer look up here, the telescope itself. So the black area here is that experiment, that dark energy spectroscopic experiment. These silver hoses are for coolant, and the black hoses, so there's one there, there's one over here. That's where those fiber optic strands go from the experiment down into cryostats a floor below this telescope. So essentially, there's a closer look at it there. This is the eyes of the DESI experiment, and down below, about a floor or two down below here, are the brains of the experiment. So there's a quick look at, and there's the control room. Part of it is a lot of vacuum tubes and dials, and other parts are more of a touch screen SpaceX sort of endeavor. But $67 million US, about $1/10 billion, and it's doing just fine. It's kind of like an old antiquated battleship that's been pressed out into service. This is sort of the cast iron version of the sort of telescope that is usually being built, and there aren't a lot of prime focus telescopes that were built lately. So for a bunch of reasons, this was a perfect, this was a match made in heaven to have this experiment be mounted on this telescope. Okay, we've got about, I think, 6 or 7 minutes left. I want to take you to the final large research telescope on the mountain. It's a little bit different. And it is the only one we actually can't see from here. But I've taken an extensive video to show you. But basically, I'll just turn you around here. We're going to be going down this road, and behind this telescope to the left and to the far side of the campus. I should mention that Kitt Peak has officially 22 observatories. Depending on what you call an observatory, it's, you could say there's as many as 26 observatories and many more individual telescopes that range in size from this little 6 here to our largest telescope, a 24-inch telescope at the visitor center, to the 4-meter Mayall telescope mapping out the universe behind me. So we had the Mayall telescope mapping out the universe, the WIN telescope discovering exoplanets. I don't have time for it, but I'll just show you over here are 2 of the Spacewatch telescopes. They are, as you can imagine, looking for near-Earth objects and hoping to give us humans a 30-year window to know if something is going to come really close to the Earth or even hit the Earth. They can't do anything about that. They don't laser blast them apart or anything. That was the original idea from the Space Guard Institute, which in fiction Arthur C. Clarke came up with, which from the book Rendezvous with Rama. But that's what actually inspired the Spacewatch system, of which these 2 telescopes are a part of. We won't have time to go into those, but I want to take you over to the largest of the Kitt Peak Visitor Center telescopes, as opposed to the research ones which we've been looking at. This telescope is the largest, until recently it was the largest solar telescope ever created, and it was divested in 2017 and handed over to the visitor center to use for public use. I'm going to do a screen share, and we'll switch over to a few views of that I took earlier today to show you, and I'll tell you a little bit about that, and then I think we'll have time for questions. Okay, there we go. So this is the McMahon Pierce Solar Telescope. It was built in 1960. It was built in the 1960s. It's 110 feet tall. It is the size and dimensions, including the length of the Statue of Liberty, if you included the pedestal that the Statue of Liberty is on. Aside from the 100-inch Mount Wilson telescope, this is the will soon be, once we reopen it to have the optics actually looking at the sun and at night the moon and planets. It will be, after Mount Wilson, the biggest telescope in the world in history for public outreach, for fun, for use, for just looking through it, for the pure joy of looking through an insanely big telescope. We're going to go inside the telescope here. I'm going to open the door up and we'll be able to see into the tunnel where the light from the heliostats that you saw at the top of that toppled over number 7 shape, which is a giant sundial, direct down through this tunnel and into a control room. So look up to the right. All right, there are those heliostats. There they are. So there's a 2-meter one, and then two 1 meter heliostats left and right there. We'll zoom out here and see the path of photons from the sun travels down this tunnel, 500 feet. Sorry, I'm used to using feet now. You can do the math in meters. We can't quite see all the way down, but 500 feet down, then all the way back up from some of the mirrors that light bounces down to these mirrors right here, and then into a control room a little further down below. There's sort of a gated off square below these optical elements, and that's where the light of the sun goes. This is an F54 telescope, and so the filtering happens simply by the amount that light travels, the distance light travels before it goes onto essentially a table in the control room, which I'll show you right now. So I've driven, it's big enough we have to drive to the other part of it. I've driven down to the lowest floor. The telescope itself goes further into the ground. We spent $4.5 million starting to build a science center in here. This will house exhibits. The reason it's so long is that this is the structure of the telescope. We didn't have any choice in what shape the science center would be. This was going to, in 2017, it was divested, was no longer able to do useful research. Researchers at this telescope discovered water on the sun, water vapor, and explored solar oscillations and various other things to do with the spectra of light from the sun. There are the control mechanisms. This is the main control room table that light from the sun would go onto through spectrographs, although it's just going to be going onto a flat table. From this square area here, this opens up, light from the sun goes from the heliostat, the main heliostat, down from mirrors down onto that table there. And this not only shows the light and light spectra of the sun, but the moon, bright objects at night as well. The best view of the moon maybe in the world is available from this telescope. So we're excited to get the optics back to show it. We can't see the sun right now until we get the heliostats working, but we can travel to the sun by going to, oh, we turned it off here. I'll go to another part of our tour where it's back on, by going to our one and only so far functioning demo, exhibition, I should say, at the Science Center called the Windows on the Universe Center within Solar Telescope. So I jokingly call a reverse planetarium. We do have plans to build a planetarium here as well. This is the Science on a Sphere. Excuse me, a bug just went into my, swallowed a bug. That's the beauty of live being outside amongst the telescopes here. Science on a Sphere, and I'm just controlling it here so you can see we're control the whole world, moving the Earth around, but we can go to the sun. We can go to things like the king of the planets, Jupiter, and see it and just orbit around it and show different elements of the environment, ocean currents and temperatures, the aurora, but also, like I said, we can go to the moon, for example, and we can orbit around the moon, go to the far side of the moon. The view of the moon from this telescope is so spectacular, that the Apollo astronauts trained here, all of them, during the 1960s and 70s before they landed on the moon. And finally, this is a view of the DESI survey, and this is very cool. This is the first time this has ever been shown, mapped out in a three-dimensional way, three-dimensional view of the universe on a three-dimensional stage, basically. I'll put that back just for a second, just to talk about that for another couple of seconds, and I think hopefully there's time for Q&A. I just think this is so cool that a telescope on this mountain that the Science Center is on made this map of the universe, this map of the expansion history of the universe. Blue is close, red is are the farthest galaxies, and this is sort of the sweet spot where we're flying in towards the part of the Milky Way that we were able to get through this. And this was all done in-house. The telescope discovered this, and now we're displaying it on an outreach endeavor in-house. And I'm just really excited with that. So that's some of the new things that are happening at Kitt Peak. And I hope I've left some time, maybe a few seconds or a minute for some questions. I see a lightning flash, but we don't have any shelter-in-place warning, so I am technically still okay right now.
Good.
Yeah. Any questions about anything that we've gone to look at and go through?
Sure, absolutely, Peter. Well, first of all, thank you so much for taking the time to present to us. On-site live presentations are great, especially this kind of topic. So thank you so much. We definitely have time for presentations, and I'll turn it over to Ennio to ask them.
Okay. Hi. So our first question is from Ronan of Stag. Is dark energy like dark oxygen?
Oh, that's a good question. I don't believe so. There's basically the missing stuff in the universe is basically dark matter and dark energy, and together those are about 95% of the universe. Only about 5% of the universe is what we can see and measure, but I'm not too sure about dark oxygen. That's a good question.
So our next question is from Zapfan. How large a field of view does the galaxy watching telescope have with its prime focus?
Okay, I'm going to go back to the visual for that. It is, off the top of my head, I believe it's 4 or 5 degrees. I'm measuring that in full moons, but I'll go back to the graphic here. There we go. I'll screen share this. Okay, can you see this?
My video is
Awesome.
frozen, so
All
I
right,
can't see it.
Okay, so basically that is about the amount of sky compared to the full moon that dark energy spectroscopic experiment, which looks like that, looks at a time. So it's quite a large amount of sky.
Our next question is from John Wonder.
I would guess off the top of my head it's probably about 4 degrees. Oh, sorry.
Oh, no worries. Our next question is from John Wonderwick. How do ground-based telescopes and space-based telescopes complement each other, and are there research projects that use both?
Ooh, good question. I'm going to turn around to show you rather than tell you. I'm going to roll the dice and unplug from the power here. I've got to duck under the steel girder, so pardon me for a sec. Okay. There we go. So there's the wind telescope there, right over there. And so I'm excited to talk about that while we're talking about this. I'll show you this telescope that's actually involved in that. Now, first of all, and I'm not the world expert to talk about this, but ground-based astronomy, I think since the age of adaptive optics that to a large extent counteract the distortion of the Earth's atmosphere. You can have telescopes that are many times the light gathering ability and the power of something like Hubble or even James Webb down on the Earth. There's still, in a lot of ways, no substitute for telescopes that are out in space, though. The telescope over here, the Wind telescope, which is mapping out or basically identifying the masses and densities of existing exoplanets, is working with the TESS Space Telescope survey that has already found those exoplanets and basically taking those planets that have been discovered by that space telescope and where their masses and densities aren't known, and measuring their masses and densities. So we not only know that they're there, but we know more about them.
And our last question is from Eric Briggs. And his question is the Atom Block Telescope at Kitt Peak that is used for public outreach? Has Dietmar used this telescope?
Oh, I'm not too sure what that is. Sorry, the what telescope?
The Atom Block Telescope.
That is, as far as I know, not a telescope that is at Kitt Peak, but we do have, I will tell you, we have 6 public observatories. We've got this one right here, which is our roll-off roof observatory. It's just starting to rain right now, so this is perfect timing. I think we'll be able to wrap this up before it gets rainy. And then we've got behind us, right over here, is one of our domed observatories. We also have just behind this dome right here, called the Burrell Schmidt Dome, is our 20-inch public outreach. Oh, there we go, our 20-inch public outreach telescope. And down just through the hedges here, where you'll see over here, you can just barely see part of our solar telescope right through that hedge there. There's also an additional telescope plus an additional solar telescope. So we've got a total of observatories with 11 total telescopes, including a number of large hydrogen alpha telescopes, calcium solar telescope, and a large number of photographic and visible light telescopes that range from, I guess 16 isn't our smallest size, range from about 2 inches to 24 inches. But sorry, yeah, I'm not too sure what that other telescope is. It might be another observatory, but if I'm wrong, I'll ask around. But I've not heard about it in 6 months. Having said that, I got shown an observatory that I didn't even know existed a few weeks ago here, because there's so many telescopes here. So that's not to say it isn't here. I just haven't encountered it yet, perhaps.
Awesome, thank you. And that's all our questions.
All right.
All right. Well, my pleasure. Glad to be speaking with you guys here.
Thank you very much, Peter. Good night. All right, perfect. We'll move on to our next speaker, and that's Pavel Krasnopolski. And the title of his presentation is Beware the Red Light. Go ahead, Pavel.
Thank you. So my name is Pavel Krasnopolski. I am connecting from North York here in Toronto. And that's actually my second presentation for the Recreational Astronomy Nights. And some time ago, I asked myself a question of, well, we all know that it's recommended to use red light when going stargazing or doing amateur astronomy. So exactly how red should it be? And what kind of intensity it should be? And so I decided to take this kind of a deep dive into the workings of human eye and any kind of theory and numbers that I could probably come up with to quantify how appropriate different lights are. And so first I'll show some small demonstration here. So suppose you actually want to go stargazing. You heard that you need to use a red light at a dark sky site. So you probably look around your home and maybe you'll find something like, maybe like this bicycle light, right? Which is kind of red. I think you can see that it's red. And well, it's a red light. So is it good enough? Well, let's see. I will just dim the lights for a moment here, and I'll have a white surface to project the lights on. And so let's just project it here. So it's kind of red, yes. But here I have another source of light, and I'll talk about it later. And you can see that those are very different shades of red. And in contrast, the bicycle light looks almost yellow. So how bad is it? Is it no good, or maybe it's just good enough? considering you already have this light, I assume. Well, let's find out. So let's go back to the slides. And right there on the title slide, you see that was the picture that I took a month ago of the Carr Astronomical Observatory that belongs to Royal Astronomical Society of Canada. And you can see the whole facility uses dim red lights throughout. You can even see the telescope sticking up, looking into the sky there. So let's get to it and let's see why astronomers use this red light. In today's talk, first we'll need to discuss how the human eye works, how it adapts to darkness, why we need the red light, what are different sources, what are our options, and how those different sources of red light compare to each other. We'll try to compare and contrast them and maybe rank, find some hard numbers to rank them. And some options for actually getting one, maybe making one even. So let's start. You might have remembered from your high school science lessons that human eye contains two types of receptors, cells that are sensitive to light, rods and cones. Rods are larger, which makes them more sensitive to very low light, so they capture much more light per each cell. On the other hand, cones are much smaller, but they give you better resolution. Chances are right now you're watching this presentation with your cones in your eyes. You will, of course, need rods to during stargazing because it involves very low levels of light. But occasionally you might also want to use your cones to read text or sky charts. And yes, on a couple of occasions I dropped parts from that very telescope that's behind me in the tall grass under dark skies, and I needed to find them. So that's why you kind of want to have both possibilities there. Here you can also see the spectra, the sensitivity of the three types of cones and rods. Right, there's only one type of rods. They're not sensitive to color. And you can see that rods are sensitive to a narrower spectrum of light. So how exactly does the eye adapt to darkness? How exactly does it switch between the low sensitivity cones and high sensitivity rods? So that's what happens when the level of luminance or illumination changes. We're dealing with a huge dynamic range, right? So between starry night, you can see it's 10 to the minus 3 candelas per square meter, just a unit of amount of light. So this is 10 to the minus 3. You can go to the sunny day, which is about 3 times 10 to the 4, 30,000. So that's already a dynamic range of 30 million there. Actually, 300 million. But the eye can also withstand even higher amounts of light. You can briefly look at the sun without permanently injuring yourself. And you can also see in a very dark room without a starry sky around you at even lower illuminations. So we are definitely covering dynamic ranges of 1 billion and more. The very first mechanism by which the eye can adapt to darkness is by dilating the pupils, right? So this line here and this chart here shows you that the area of the pupil can increase 10 times. But this controls the amount of light to all of your retina, to all of your sensitive cells. So it doesn't really differentiate. And when in a very low light, this is called scotopic vision. And you only have your rods working, really, and your cones work at very high amounts of light. That's called photopic vision. So exactly what happens when the level of light changes? You can see it on this graph. On the horizontal axis, you still have the amount of light, luminance in candelas per square meter, logarithmic axis. And on the vertical axis, you see the sensitivity. Now, that's interesting because when you go into high levels of light, you can see the sensitivity dropping almost inversely proportional to your luminance, which means basically your eye wants to give the output in the same range. The signal that it sends to your brain should go, let's say, from 0 to 100% all of the time. And so if the amount of light is a lot more, then it has to turn down the sensitivity just to keep it within the range. And the thing is that cones start saturating and tuning down their sensitivity at much higher light levels. Roughly, this boundary is the upper boundary of the so-called mesopic vision, when you have the mixture of the photopic and scotopic visions. And of course, the rods start saturating at much, much lower light levels. In fact, the starry night here, which is something that you will experience during stargazing, the rods will already start to saturate a little bit, by maybe a few percent. So they can actually detect even lower light levels. And notice that the sensitivity is 2 orders of magnitude difference here. Of course, rods are much more sensitive. And from my experience, I actually measured it. To be able to read the text, I need about 0.3 lux of illumination. On a white page, it would give you about 0.1 candelas per square meter of luminance. So we're talking right about the middle of mesopic vision is what you need to just start to be able to read small text or see fine details. So that's where your cones roughly kick in and they start working. However, we have a paradox here because, of course, for stargazing, you need more than 100 times lower light level. Sorry. So here's what I want to read. Here's what I want my cone response to be. And here's what I need to stargaze. So here's what I need my rod response to be. Right? And of course, if I just shine a white light at 0.1 candelas per square meter, then I will saturate my rods by, well, about 30 times here. So which will be absolutely disastrous for my night vision and for ability to enjoy dim objects in the sky. So how can we have both of the worlds here? We need essentially a range of 100 times a difference between the rod response and the cone response. Well, the key to this is noticing that in the red light, so 650 or so nanometers, cones have significantly more response than rods. Even as you see the rods and cones curves adjusting to the light levels, still the red light is mostly the area where the cones really outperform rods. And even in the very, very low light, even under the essentially dark sky, the sensitivity of rods and cones is essentially the same, despite the overall sensitivity being 100 times difference. Which tells us that we should use red light. This is the primary reason. That's essentially the way to cheat around the different sensitivities. And if there's one thing that I wanted to remember from this presentation is this chart here. So what I did was I took the curves of sensitivity of scotopic and photopic visions, mostly rods and cones, from the website of International Commission of Illumination. They have reference spectra for a lot of things. I scaled it to 100. Again, because we saw in the previous graph that the relative sensitivities can change a lot with changing light levels. So the absolute values here don't matter very much. We can basically just normalize the peaks to 100. And then I plotted the ratio between them. The idea is that we want a certain amount of cone response. So we want to find this kind of the type of red light which produces the minimum rod response, the minimum possible one. So you would have the ratio of the rods to cones responses at the minimum. And you see this black line here, which is supposed to tell you that. Now, there are several lessons to learn from this. So first of all, the light at 680 nanometers wavelength is pretty much as good as it gets. There is almost no sense in going longer wavelength. You will only lose overall efficiency because, of course, the sensitivities keep dropping with longer wavelengths. So there's no point of going longer wavelengths. And if you go into shorter wavelengths, 660 nanometers is still mostly okay. It's a change of about 25% here. But then it starts deteriorating rapidly. So the rods will start picking up more and more light here from your flashlight. So these are the vertical lines here are different types of LEDs. And I'll show the comparison between them later. And there's also another way of creating red light, of course, is by using a filter. Here I'm using a particular type of filter, again, which I'll show in a moment. And the spectrum of it is shown here in dotted lines. Please note that this is a logarithmic scale. So the maximum here is at 80% transmission of the filter. Now, half of that would be 40%, and that happens at 660 nanometers, which is roughly the cutoff wavelength for practical purposes. It has just a tiny tail of transmissivity here at about 2%. It doesn't affect the situation too much, and so we'll see in a moment. And just a little note about the LEDs here. So there are different wavelengths of typical LEDs that you can buy. Here's their, again, a collection of spectra of different LEDs. This one is the most common. It has the peak at about 630 nanometers, which is also the bicycle light that I showed earlier. But there are also others. Those are the ones that we probably want. Please pay attention to this shape of those spectra. There's quite a lot of light at shorter wavelengths. And of course, the sensitivity of the eye increases with shorter wavelengths, which is why, despite having a peak at 630 nanometers here, the LED actually will have an effective or so-called dominant wavelength at about 620 nanometers. And for example, these ones, if you have a wavelength of 680 nanometers, the dominant one will probably be around 660. So now let's compare all of the ways that we can produce the red light. So what I did here was essentially took a table of the spectra of sensitivity of the eye, and also spectra for some other things like incandescent light bulbs, like white LEDs, also multiplied by the transmission of that filter that we showed in the graph, and just bare white LEDs. And so those numbers, those are those ratios of rods to cone sensitivity. You don't need to pay attention to the absolute value of this number, because again, it's somewhat arbitrary. Both sensitivities were scaled to be 100 at the peak. But what you should pay attention to is how those numbers compare between different sources and different wavelengths. Right? So the red LED, which is marked as peak wavelength 680 nanometers and dominant wavelength of 660 nanometers, is almost ideal. It's just about 25% worse. There's also the types of LEDs that are sold for example, grow lights, for also deep red lights, for example, photographic processing, photo red. They're called different things, but they're all have a peak at 660 nanometers. Those are somewhat worse, but still generally tolerable, right? And then you can go to other options. You can have incandescent lamps with a filter. You can have the common red LEDs, again, right, like in the bicycle light that I showed you. You can have white LEDs with the filters, and those progressively get worse. Already the cool white LED with the temperature of 5000 K will be about 7 times worse than the ideal, and more than 5 times worse than the 680 nanometer LED. And of course, just pure white sources are absolutely terrible. Please do not use bright white lights at, for example, dark sky preserve or any stargazing location, because you can see those numbers are more than 100 times worse than ideal. So you have this, actually another way of putting this, if the white light produces about the ratio about 1/2, and your red LED produces about 0.005, that means that you have that 100 times improvement over the white light of the sensitivity of rods and cones, right? The ones that we said we need to simultaneously use actually both rods and cones, be able to read a sky chart and be able to stargaze. So let's look at those sources. So first of all, I'll show you the filter. So this is a particular type of filter. It's used in stage lighting. It's usually sold in those sheets, 24 by 20 inches. There are several companies making them, and there's a huge selection of different colors and different types. But this one, number 787, called Marius Red, is the only one that I found that has this good spectrum with a cutoff longer than 650 nanometers. And it looks very, very dark. Here I have even a thinner strip of it. You can see that you can still see the my lamp through it that I have in my room, but it's quite dark. Despite having transmission of 80% in the deep red, it cuts off everything else, which is why it's dark. These are usually available quite cheaply for about $10 for that piece, depending on your source. Now, there's also, well, I've already shown the red 635 nanometers or so light, like this. Your other option would be to take a white light, like this one or like this one, and then cover it with a layer of that red film. Right? You can see how much the red film decreases the overall brightness, because it cuts off all the wavelengths there that you don't want. And of course, you can go for just pure 680 nanometer LED, and that's the source of light that I showed in the very beginning, right? That's here I just have a simple module here attached to some wires connected to power with a bit of lens there. That could be an option for if you're more inclined towards DIY options. Those LEDs can be sold, well, they can always be sold as just usual 5 or 3 millimeter LEDs like this. But take note that these are not very powerful. Sometimes you might need currents that these LEDs are not capable of, and you can buy more powerful LEDs, sort of something like this. It's a heatsink mounted module, and then work with that. And then, of course, there's a huge selection of different lenses. Usually, they can be found very cheaply for large packs like this. So let's see how this chart works in practice, right? So I'll just bring back my stand here, and we'll set out the light sources from the worst, like this white, cool white LED flashlight, from the worst through the kind of okayish to good and to the best. Right, so once again, this is, you have the white LED, absolutely terrible for stargazing. This is red bike light, just any kind of red light that you would find around your house. This is the filtered white, using that gel filter for stage lighting. And this is pure 680 nanometer LED here. So let's take the sheet of this filter, and let's see what it does to these lights, and pay attention to the intensity, right? So immediately you see that it cuts a lot of light from the bike light, and it cuts a lot of light from the white flashlight. But if you look towards the better options here, the change of light is actually quite minimal there. So we can tell that the filtered white and pure 680 nanometers LED are actually pretty good. There's almost no reduction in their brightness, which means they already have just the good wavelengths that we want to work with. On the other hand, the bike light, despite technically being red, you can see a lot of that light gets cut off, to the extent that the brightness of the bike light is almost the same as the brightness of the white LED through the filter. And the reason for that is that this LED, this sort of red LED, doesn't actually have the wavelengths that we're interested in. If you go back to the to our spectra there, right? This is the bike light here. We want spectra that's we want wavelengths that are longer than 650 nanometers, but it doesn't have any, almost none. Which is why when you filter it, you cut off so much light. And so there's basically no advantage of starting with a red light if you are going to filter it. Now, of course, if you don't want to filter it, then having at least some kind of red light is still better than nothing. So let's summarize, right? What are our options? Cheap and quick is the red filter, and you saw that yes, indeed, we can use it and obtain pretty good spectrum. They are called gel filters. They used to be made on gelatin, but now, of course, it's just cellulose acetate. About $10 per pretty large sheet. This is the only type that I found which is suitable, 787 Marius Red. You can use it on white LEDs. You can use it on incandescent lamps. You can use it on your phone screens. It's pretty good for that. Using it on red LEDs is, well, frankly, doesn't make much sense, in my opinion. And it does cut off a lot of light. So you might, paradoxically, you might need stronger white source, despite wanting to achieve a dim red source. But because so much light is getting cut, you might need to start with a brighter white source. And unfortunately, it's usually difficult to contain the stray light. You will need to use a lot of dark tape around your light, because even small leakages of white light will probably ruin your picture, because that white light is much stronger than the red that goes through. Now, not as cheap, but still cheap. Common red lights, like the bicycle light that I showed. It's better than nothing, but the wavelength is too short. So we saw it's at least twice worse than the ideal. Slightly better than filtered white. And another thing I found is that it's just way too bright by itself. That bicycle light had to be dimmed about 3 times before I was kind of satisfied with the intensity of it. And I did test it in a dark sky area. You could use the filter, but only to make it dimmer, essentially. Now, the best ones would be, well, second best ones would be the 660 nanometer LEDs. They're used for grow lights, etc. It could be good enough for most purposes. The advantage over the longer 680 nanometers is that usually it's easier to find, usually easier to source. And of course, at those wavelengths, you don't need a filter. And the absolute best, of course, is the 680 nanometer LED. It's almost ideal. Usually, you would need to buy them in, well, modest bulk, maybe 10, 20 at a time. Yeah, so for the if you want to experiment with it yourself, and you want to actually source them, here's some of my recommendations. I actually tried all of this experimentally. Sorry about this. I found the best lens is the 30 degree angle lens. This is the lens that I have on the actual LED that I just showed. When you have the lens with the reflector, it usually outputs more of the light and doesn't produce as much of a stray light. With these LEDs, I found that the current of about 30 or 50 milliamps is good for walking and seeing several meters ahead of you, including seeing the grass and being able not to break your ankles. And you can use the dimmer lights if you just want to read sky charts. So for the just for reading, you would you could use a single small LED, which they usually go up to about 20 milliamps. And for slightly brighter purposes, you might need a bigger LED, or maybe a couple of smaller ones. So this basically is all that I have today. I'll take some questions.
Great. Thank you so much for your presentation, Pavel. It was great to learn about the theory and then to see the actual demonstration. So well done with your presentation. Thank you again. Anya, do we have any questions for Pavel?
Yeah, we have a question from Betty, who asks, what manufacturer and what supplier can you recommend for the 787 Boreas light?
So usually those sheets are made by well, two major companies. There is Lee Filters and there is Roscoe. They both cost about the same, and the spectra are nearly identical. So it's more or less standardized. So again, Lee Filters and Roscoe is what I kept finding. The one that I have here is from Lee Filters. There are several stores around Toronto. I'm not sure if it's to be appropriate to say those right now, but yeah, there are some stores. I mean, usually the search the keywords that you want to type into, let's say, Google, it's just the 787 Marius Red, and yeah. Again, do you want me to give examples of where to buy them?
Sure, I think that'll be fine.
Okay, well, there's one place in Etobicoke. It's called Source Shop, the Source Shop, with the same website, sourceshop.com. And you can buy anything from the 24 by 20 inch sheets there to 25 feet rolls. Of course, bulk orders are cheaper. That's just the ones that I bought those from a few years ago, and yeah, it's usually within about $10 per this sheet.
Okay.
And we have a comment from John Wunderlich who says, "Nice and effective demonstration. Thanks." Followed by Betty with, "So true. It would disentangles the question of which lights are best and why."
So which lights are best and why? Essentially, this table is supposed to summarize it, right? I would say if you want to just put something together quickly, is you would use a filtered red. So you would use that filter, and you would tape it onto a white flashlight like this. But again, make sure you check it, because the white flashlight should be sufficiently bright initially, because when you tape it over with the filter, it becomes quite dim. So this is easy to make and very quick. You do need to buy the filter. Otherwise, well, if you look on web stores, Amazon and like, there's a lot of flashlights that are called for astronomy, for stargazing, and dark, etc. If they don't specify the wavelength that they have, assume that it's just the cheapest 630, 640 nanometers, like this one. So it will not be as good, but it'll be better than nothing. So do go with just red flashlight if you don't have anything else. Try to find something that specifies a longer wavelength in the description of the product, or use a filter.
And our last question is from Ronan of Stag. "Sorry if you went over this already and I couldn't parse what you were saying, but what is the difference between the initial red light you shared and red shifted, please?"
So the initial, I guess it's what was the initial comparison that I did in the beginning. So again, this is the most common one that has the a wavelength of 630, 640 nanometers, and this one is 680 nanometers, right? So when you have a dedicated long wavelength LED, you don't need to filter it. You can basically just use this as your flashlight. With this one, you might try to filter it, but it will still be a bit inferior. And again, if you go back to the chart in the presentation, you see that this most common LED is about 3 times worse than the 680 nanometer LED. So for the same amount of the response of your cones, if you adjust the brightnesses of all your flashlights to produce the same ability to read text or work with small parts, then the common LED will have 3 times as much effect on your rods. I guess that's the main lesson to learn from this.
Okay, thank you.
Okay. And one of our AV technicians, Ward LeGros, mentioned to me that he also has access to these gel filters, and he would be able to supply them to our membership for a cost, I imagine. So again, Ward LeGros, you can probably catch up with him at our next meeting, which will probably happen in person. So Pavel, thank you so much for the demonstration and the presentation. We'll now move on to announcements from our president, Tom Luden.
All right, and thank you very much, Paul, and thank you very much to all of our speakers for a wonderful evening. And let's get on with the announcements. So those of you joining us live here on YouTube, welcome. What you've just seen is one of our recreational astronomy nights, and during the non-summer months, we also have a number of speaker nights. Those of us who are joining us live, please use the YouTube chat to say hello, to enter some questions for presenters, as others have already done. If you're a new member to the Toronto Centre, please introduce yourself. And if you're coming to us from far outside the Toronto area, please let us know where you're coming from. By the way, tonight I'm speaking to you from my couch in downtown Toronto. So, as Paul alluded to, it's our intention that our next recreational astronomy night will be in person and online, and we're hoping this. So on Wednesday, September 4th, 7:30 p.m., Claudio Oriani will be talking about the sky this month. Charles Young will be talking about DIY power for your equipment at a dark sky site. And we currently have one more presentation slot available. Please drop Paul Markov a line at pmarkov@rogers.com if you'd like to present something. So, where are we meeting? The answer is our new home is going to be York University. So I'd invite folks, it's our intention to have this up and running for the first Wednesday in September. Please join us if you can for our first in-person RAN at our new digs. Room 317 of the Petrie Science and Engineering Building at York University. This is the same building that houses the Alan I. Carswell Observatory. This room is just down the hall. And this makes finding it very easy because the building is covered in signs for how to get to the observatory. So literally follow the signs for the observatory and we will plant our own sign right in front of the observatory doors, pointing you in the direction for the meeting room. Full directions and dealing with things like transit and parking will be posted on the website shortly. So please join us. And our speakers nights will also be starting up in September. We'll have the details for you when we get them. Now, coming up with events in the month of August. This Friday, August 9th, from 7 p.m. to midnight at Millennium Square Public Stargazing. Please join us for an evening of free public stargazing along the North Shore of Lake Ontario at Millennium Square in Pickering. You can observe the moon and stars through our telescopes and check out our astronomy literature and ask us some questions about the stars and planets. And if you've got your own little telescope, we'll be happy to help you set it up and name it at the moon. Remember that things are cooler down by the lake, so dress appropriately. And please check our website for a go, no-go decision based on the weather before heading to the square. Coming up the DDO this month, also on Friday, August the 9th, from 9:30 to 11:30 p.m. Is Astronomy Family Night. You can register online. The fees are as listed here, and the links to the registration can be found at rasctho.ca. On the first clear night of the week of August 12th to the 16th, that's the first clear night, starting at sunset, is DDO Stargazing Night. So please bring your own binoculars. No registration required for this event. Just walk on in. Then we have another astronomy family night on Saturday, August the 24th, 9:30 to 11:30 p.m. Again, registration fees are as seen here, and again, links can be found at raxto.ca. And wrapping up the month of DDO is Sunday sun gazing on August 25th from 12:30 to 1:30 p.m. Again, fees as shown here, and links can be found at raxto.ca. The CAO is open. Operations at CAO are working back to pre-pandemic conditions, and masking in common areas is encouraged, but is the preference of those in attendance will be taken. Please read the CAO bookings page for all the details before you make your booking. Just a reminder that the Toronto Centre runs on clean, renewable volunteer energy. If you're a RASC Toronto member and if you're interested in helping out and you've got some free time, please drop a line to volunteer at raxto.ca. Just a reminder for those of you who are volunteering, and if your employer is part of the Benevity program, RASC Toronto Centre is now working with Benevity to receive charitable donations. So if you, like I said, if you're a volunteer and your employer has signed up to make these contributions, please let myself or our treasurer know so that we can get those funds moving. This is where I get to plug the joys of RASC membership. For those of you who've been watching us, if you've liked what you've seen, if you'd like to be a part of what the Toronto Centre does, if you'd like to share astronomy with the world, you can sign up or renew your membership online at secure.rasc.ca. Gift memberships are also available. Contact the national office at mempub@rasc.ca for more details. And with that, I'd like to wish you all a very pleasant evening. Thank you very much for joining us. Please follow us on all of the forms of social media we've got listed here. For those of you watching us live, if you like what you saw, please like and subscribe and hit the notification bell. Stay safe and keep looking up. Good night, everybody.